started?
I'm ready.
Okay. Welcome everyone to the second day of this workshop. Thanks for coming in the morning. And we're happy to have Jonathan Leake. He's going to tell us about continuous maximum entropy distributions.
Okay, thanks, Cole. And thank you to the organizers for inviting me to give this talk. I had planned to be there in person. Unfortunately, some bureaucracy there were some issues, but in any case, I'm still going to give this talk, and feel free if you have any questions just to interrupt me at any point and I'll try to answer them. Okay, and this is joint work with Nishith, and let's get started. Okay, so I'm going to start off with a question here. The question goes as follows: suppose we have some subset of R to the D, call it M, okay? And let's let K denote the convex hull of this M, and let this capital A be some point in this convex hull. So these three letters we're going to use throughout the talk for these kind of things. Okay, suppose we have these things. So here's the question: is there some canonical way to express A as a convex combination of the points in M? And I put convex combination in quotes here is because really what I'm looking for is some probability distribution on M whose expectation is A, right? Of course, there are many ways to do this. Is there some sort of natural one or some canonical way to do this, to choose this? Okay, and if we suppose that M is a discrete set, so let's say some finite set of points, which we'll see a picture that's more relevant to that case in a second here, but if we suppose that M is discrete, then there is sort of an answer to this, which is basically, let's choose the distribution on this discrete set, which maximizes the Shannon entropy. So we would look at all distributions with expectation A, and we would choose the one that maximizes entropy. Okay, and this was already this idea was given by Jaynes in the 50s, so quite a long time ago. Okay, and so naturally these distributions that, if we pick such a distribution, we're going to call it a maximum entropy distribution. Okay. This is also generalizable. I generally won't really refer to this generalization that often, but I mean, one thing that you could do is somehow maximum entropy distributions are related to the uniform distribution, say on this set of discrete set of points. But if you somehow had like a prior distribution, some kind of information you had extra that you wanted to add in, you could also, instead of maximizing entropy, you could minimize relative entropy with respect to this prior distribution. But up to this detail, basically, you're still kind of maximizing entropy. And so I'm just going to be using this term maximum entropy distributions throughout. But just know that if you have a sense of what this Kullback-Leibler divergence is, you can also minimize relative entropy with respect to some other distribution. Okay, anyway, but in this discrete case, there are already a lot of applications, which we're going to see exactly. I'm going to give you some more concrete details about this, or at least some references. Connections to combinatorial inequalities, discrete approximation, this very recent new improvement to the metric traveling salesperson algorithm approximation is related to this. And then there are some other examples which we've either already seen this week or maybe we'll see later this week, related to scaling algorithms, orbits, and also to statistical models. Okay, but so maybe we have some applications here. This is then maybe something we want to think about. The question is, how do we actually compute this, right? This is some optimization problem over a set of probability distributions. And maybe if this set M is quite large, maybe this is difficult to do. So how can we do this? Okay. So now here's a picture more relevant to this discrete case. Okay, so now suppose we have this M, this set of these black points here. Okay, K is the convex hull, this gray area, and now A is some point in the convex hull. Okay, so this is our discrete situation. Okay, and so this primal problem that I've written down here is exactly the maximum entropy optimization problem. So this is exactly what I was describing before. This quantity is the entropy of some distribution mu, okay? And I'm looking for the maximum over all distributions supported on M that have expectation A. So this is exactly right. The optimal mu here is exactly the maximum entropy distribution. It turns out that there is a convex dual form to this, which can be written like this, okay? And the key, actually, I'll say that in a second. So basically the idea then is, in this discrete case, this dual program can be efficiently computed. You can efficiently optimize this using the ellipsoid method, as long as basically you can compute these sums efficiently. Okay, and this discrete case. There are some previous results of Nishith and co-authors here. But the things that's important to think about when you look at this, right? So okay, so I have this primal problem. This is the maximum entropy problem, right? A priori, this entropy is some concave function. So doing convex optimization here is not hard. One can do this. The problem is often this set M is quite large. So if for instance, if you look at this picture, the set M has maybe like a huge number of points compared to the dimension of the ambient space, which here is just 2. Okay, and so what this primal dual pair allows you to do is to optimize something that's somehow much smaller. The search space is much smaller, and that's kind of the first observation here. By going from primal to dual, you can shrink the search space dimension quite a bit. Okay, and so this can enable you to do things a lot more efficiently than if you just looked at this naively. Okay, the other thing that this gets you is a very special form for the maximum entropy distribution. Okay, and the reason why you can even solve the dual program to get the solution for the primal is you have some kind of strong duality relationship, right? That says that the solution to this problem is equal to the solution to this. And what that also gives you is somehow now this maximum entropy distribution has to be very related to this optimal y. And that's exactly what this says, right? This says that maximum entropy distributions are always of this log linear form, e to some linear function. Okay, this is some particular, this log linear function here. Okay, and another comment I will make here is that if you kind of transform this a little bit by maybe exponentiating this objective and maybe exponentiating some input here, you end up getting this polynomial capacity problem. In fact, this dual is pretty much equivalent to polynomial capacity with this very easy transformation. It's very easy to see the connection here, but I will also mention this other work of Nishith, which is different than this one, which kind of gives a little more kind of detail about somehow the entropy interpretations of this optimization problem here, this capacity problem. So this is also related to like the Bethe approximation, if you know what that is. And so there's a lot more connections here. There's a lot deeper connections. Okay. So this discrete case has been solved before by previous works. It has this connection to capacity. Okay, why do I bring up this capacity? Okay, so we saw that this discrete maximum entropy is sort of in very strong relation to polynomial capacity. And if you know me or you know the things I like to think about, I like to think about this polynomial capacity quite a bit. So I wanted to give you this aside of all the different places that it appears. And so, discrete maximum entropy programs or some generalization also appear. Okay, so here's the more general definition, right? This is what I said before. You have this infimum. You have some polynomial here divided by some just product of monomials like this. Okay, this original definition is due to Gurvitz, and it has all sorts of applications. Okay, so the original use of this, and implicitly the original use of these discrete maximum entropy programs, well, okay, not the original use, but at least through this capacity, is connections to the permanent, to approximating the mixed discriminant, the mixed volume, some other combinatorial quantities like integer points of polytope, volumes of polytopes. Okay, there's quite a bit of work on that. There's also quite a bit of work related to doing optimization and some kind of counting on matroids. So if you want to count the number of bases of a matroid, or you want to count the intersection of two matroids. And also, like I mentioned before, this very recent work that improved this approximation factor for metric TSP in general, made use of capacity, and capacity was crucial to the analysis there. Okay, but then beyond kind of connections to polynomials, there have also been a number of generalizations of capacity, which we saw yesterday and we'll see throughout this week. There are this capacity problem, it turns out, can be generalized to some kind of norm minimization problem over certain orbits. Okay, and this is very related to these matrix operator and tensor scaling problems. There's a lot of work done there, and there's no doubt that I've forgotten some work here. So if I've snubbed you, please say something at the end so I can, or even now, so I can make sure to include you there. These orbit intersection problems. So you want to know when two orbits intersect, or null cone problems. And also this kind of framework of non-commutative optimization is very related to a certain generalization of capacity, and also to statistical models, which we'll see, I think, at the end of the day today, at least one talk about that. Okay, so the point here is that, right, these discrete max entropy problems, there's a lot of connections, a lot of applications, a lot of things known. There's even generalizations that can do a lot of things. Okay. Okay, but let's now get back to maximum entropy distributions. Okay, we saw in the discrete case, we can, given certain things, these are efficiently computable. There are many applications, even many generalizations that are already known. Okay, and so this whole talk so far has been about whenever M has discrete support. And I can ask this question of, what about non-discrete support? What, if you generalize to some kind of manifold, what do you get? And maybe the first thing you're going to say to me is, well, okay, we already saw in the previous slide, there are a number of generalizations to beyond this kind of discrete case. There are these generalizations to do, norm minimization on orbits, maybe orbit intersection. Like, what are you talking about? What do you mean generalizations to non-discrete support? Okay, but the point is, actually, those generalizations from before are kind of different than the one we're going to consider here in this talk, which is specifically generalizing this idea, this connection to maximum entropy distributions. And I'll say this at the end, but it's sort of a kind of a conceptual open problem, whether or not the generalization I'm going to talk about today is so how connected it is to these other generalizations that deal with invariant theory and statistical models and all of this. Okay, so let's get back to this problem that we started with. Okay, and now we're going to consider M to be some manifold embedded in Rn. So at first it was some set, we restricted to some discrete set of points, and now it's going to be some manifold. Okay, K is still going to be the convex hull. This makes sense because, this is embedded in some RD, so convex hull makes sense here. And we're going to, again, pick some point A in the convex hull. Okay, and we want to find some natural distribution on M, which has A as its expectation. So let's just sort of naively write down the thing that we had before, except, right, instead of some sum, we'll just have some integral. Okay, so I'm just going to write this down very naively. Okay, this sort of looks like entropy somehow. I'm still taking supremum over things with the right support and the right expectation. Maybe this will just sort of work. Okay, but actually there are some problems that arise immediately when we try to write this down. Okay, probably the most crucial problem is this first one, that basically says, okay, I've written this integral with respect to X, but somehow I'm kind of assuming, right? Okay, if this manifold was open, some open set in R to the D, then this would make sense. We would have Lebesgue measure. We could put it on this open set. We could take this integral, and maybe we could get something out of this. The problem is, if we want to look at something more interesting, not just open sets in RD, it's not exactly clear how we should integrate. It's not exactly clear what this measure should be. Okay, and what this sort of means for us is that somehow this is the natural thing to write down for entropy, but because there's no sort of way to write this, or at least it's not clear what this should be, there's no canonical notion of entropy. Somehow the notion of entropy is going to depend on the manifold M through some choice of measure, which we'll see in a minute here. Okay. The other thing is, even if this worked, let's suppose like I could just write this down and put dx here and everything was fine. All of a sudden now this is a supremum over some function space, right? In fact, it's infinite dimensional. So before maybe this space M was very large, and we would have problems doing things efficiently. But here it's not even clear, if we can do this optimization because of this infinite dimensionality. Okay, so that's something we'll have to think about. And also, this is somehow similar to the previous case in terms of, right? If M is very large, there's no way we could efficiently write down all of its entries, right? Sorry, all the points in it. But now it's not even clear how we could even express M in a concrete way, right? M is some manifold. We have to give it some kind of description. We can't sort of enumerate its elements. And so these two are kind of linked. They're sort of issues with what happens when you try to go to manifolds or more continuous spaces. But this first one is the thing that we kind of really need to handle before we can even move on. Okay, so let's see what we can do about it. Okay, so here's now we're going to do we're going to add something here. I've given a different picture to maybe give you a very simple case where you might where you might think about these types of measures. So, okay, like before, we have M is a manifold embedded in RD. Okay, we have this K being the convex hull. Here, M is just the circle. The convex hull is the disk. Okay, and A is some point in the convex hull. And now mu, which is not really, you can't really picture it, right? But mu is now going to be some probability measure on M. And just for the sake of this part, you can just think of mu as being the uniform distribution on this circle. So we have some natural way to talk about the uniform distribution on this circle. And so let's just think of it as that for now. Okay. And once you have this mu, you now can write down what I tried to write down before, this primal problem. Okay. Which is just basically exactly what I wrote, except now there's this d mu. Okay. So I have mu is some measure. I'm now integrating over this manifold. And now I have this entropy quantity. Okay. And this is exactly what we would hope for, or what we would think it should be. Now, what's the thing that's less clear, but if you kind of work through the details, you'll see this. It turns out that this basically the same convex dual, you can get the same expression. Okay, with basically the difference you'd expect here, instead of some sum, you have this integral with respect to this measure. Okay. So we have this primal problem we want to solve, still infinite dimensional. This is an issue. We have this dual problem now, which is now finite dimensional. Okay, so this is sort of, it reduces the dimension in the same way that the discrete case did. Okay, and by strong duality, in fact, the solutions to these two are the same. And so now we had this infinite dimensional problem. Okay, but it turns out we can solve this finite dimensional one, and that's good enough. And as soon as we get this solution Y, it also tells us exactly what the maximum entropy distribution is. And so this generalizes this fact that we saw in the discrete case. These maximum entropy distributions, even now in this more general case of manifolds with measures on manifolds, are always given by this log linear density with respect to the measure we started with. Okay, so we now have like maybe a problem that we can try to solve. We have this finite dimensional optimization problem that's gonna give rise to this this measure that we want to try to compute. But now these questions kind of now populate. So the first one is, why do we care about this? I mean, like, okay, we can do this. What's the point? But supposing even we do care, for some reason, which I'll talk about, how do we actually compute this? Okay, we still have this integral kind of going on. Right before, we needed some way to compute sums. Now we need to be able to compute these integrals, okay, which seems harder. It's not even clear if we can do this. And also, what about the question of sampling? Suppose we can compute this, can we sample? Okay.
Jonathan, I have a question.
Yeah. Yes.
Somehow I'm just a little confused with the formulas. Like the dual, I always think of it as like it as being the dual to a relative entropy problem, but the primal, I mean, it doesn't quite look like relative entropy. Can you clarify, like, what's the difference between this primal where you're taking entropy with respect to mu and relative entropy?
Yeah, so this primal is actually relative entropy. I'm like cheating a little bit here. This nu is really like this radon-Nikodym derivative with respect to mu. So this really is like minus Kullback-Leibler divergence. I just wanted to write it in this way to make it look like entropy somehow, to give like the intuitions. But yes, I mean, this nu is really it's like this density function with respect to mu, and so this ends up being the KL divergence.
That makes sense. Thanks.
Okay. So let's look at a couple examples that might motivate us to think about this. Okay, so the first one is I'm going to refer to as quantum entropy. Okay, and so there's already a notion of quantum entropy out there. This von Neumann entropy is often used. Okay, and if you're given some PSD matrix with trace equals 1 and lambda I are the eigenvalues of this matrix, then this entropy can be computed in this way, right? There's a really nice formula for it. But you can think about this sort of as the Shannon entropy of kind of a probability distribution associated to the eigenvalues. And in fact, you can think of this as giving rise to some discrete distribution on the eigenvector pure states associated to A. So the rank 1 PSD projections associated to the eigenvectors of A with probabilities given by lambda I. Okay, so this is some very famous quantity that's used in quantum physics quite a bit. Okay, but there are certain issues with this. There's actually quite a few sort of more philosophical works, which is sort of maybe an interesting thing to say, but there are these sort of a lot of works where people kind of criticize the use of this in various contexts. Okay, and often the critique, at least mathematically, boils down to some fact that you can kind of think of this as some minimum entropy distribution, and or at least the way you might think about this is a very terse description of A. Somehow the support of this distribution that you're associating to A is as small as possible. There's even a paper that I read pretty recently, kind of from the early 90s, where basically someone is able to show that if you use that, if you look at certain, like, I'm a little bit rough on this, but it was some kind of nonlinear generalization of like quantum physics, and you looked at certain basically if you tried to compute von Neumann entropy there and use these things, like for instance the second law of thermodynamics, which says that a system the entropy only increases. For the von Neumann entropy, this actually fails in these generalizations. I unfortunately don't know much more than that, but often these critiques are related to this. You have certain generalizations of the rules of quantum physics. You try to apply things related to von Neumann entropy, and there are these issues where certain things you expect to happen break down. And often the generalization that's suggested is to, instead of looking at discrete distributions on eigenvectors, to try to look at certain distributions on all pure states. So not just restricting to these eigenvector pure states, but you want to look at some continuous distribution on all pure states. And so what this then kind of turns into, and there's this, I'll just put it here, there's this work of Slater in the early 90s, who explicitly kind of writes this down and computes for some small cases. Basically, what you do is you look at all distributions on the set of pure states, and you take this supremum over the entropy quantity, and you call that the entropy of A. And so this, of course, is just this primal problem from before. And now what's our manifold? What's our measure? Well, okay, here this P1 is going to be the set of all rank 1 PSD projections. If you think about what the convex hull of this space is, that's going to be all density matrices. So PSD things with trace equal to 1. And now there's a very natural measure on this space, which is a Haar measure. And this just comes from the fact that this set you can act on by conjugation action by the unitary group. And I'll talk about this more concretely a little bit later. But the point is, you have some unitary group action that gives rise to some very natural measure, and you can write down this expression. Okay. And like I said, the efficient computability of this quantity was shown by Slater for some low-dimensional cases, and the general case follows from our work, with this caveat that the complexity depends on the smallest eigenvalue of A. So if you're very close to the boundary, the entropy goes to infinity, and in that case, things start to get a little bit less efficient. Okay. So that's one place where these distributions appear. Another place where this type of thing comes up is in a particular place in interior point methods. Okay, so there's this thing that's called the entropic barrier function that looks something like this. You have some convex body K. Often it's compact, but I don't think it needs to be. And you look at the supremum of this objective here, and that's going to be some function. So your V is sort of the A from previous slides. And it turns out this is some self-concordant barrier function for this set K, and has optimal self-concordance parameter. This was proven by Ubeck and Eldon a few years ago. Okay. And it's very easy to see, right? The only difference is maybe there's some minus signs, and this soup should be an inf, but basically if you negate this, you end up getting the optimal value of the Max-Entropy dual program. Okay, so that's maybe even why you would call this the entropic barrier function. Okay, and in this case, now our manifold is an open manifold. It's just this convex set K, and our measure mu is just Lebesgue measure restricted to K. Okay, and there's an open problem related to this barrier function, which says, is this efficiently computable for K given as a membership oracle? And we don't answer this question, but basically we can reduce this question to being able to compute these integrals. And we're going to see this a little more. I'm going to give you something more general here in a minute. But basically it reduces to being able to compute these integrals. And then there are certain, for certain choices of K, there are maybe certain sorry, what am I trying to say? There are certain algorithms for computing such intervals. There's also a caveat about if V gets too close to the boundary that has to be thought about as well there. But for the most part, this kind of, our algorithm reduces this to being able to compute these intervals. Okay, and beyond these two things, there's also some other connections, which I'm not going to be able to really talk about that much. There's some connections to the isotropic constant, which this is sort of maybe a little more of a hazy connection. I can't say anything too concrete here. It's just that certain integrals like this appear in this work of Klartag in the 2000s. And there seems to be some connection. It's a little bit, I can't say anything too formal there. There's also some distributions on matrix spaces, which are basically maximum entropy distributions. In particular, these Bingham distributions, I think are I guess they're a little bit different. They're distributions on the sphere that can be derived from these max entropy distributions, and they appear in things related to like distributions representing like magnetic fields on the surface of the Earth. So these are used in like some interesting applications. And there's also this kind of cool connection related to this Gomans-Williamson work on the max cut problem, where, I mean, so the way that they kind of get approximate solutions for this is they do some kind of semi-definite program. They get some positive definite matrix out of this, and then they do this thing where they try to round this positive definite matrix to some vector. And basically that rounding that they do at the end of the algorithm, they do it randomly. They draw from some distribution, and it turns out that the distribution they draw from is a maximum entropy distribution. So these things are kind of around either implicitly or explicitly in a number of places. Okay, and so we talked about a few examples here where these things come up, but the other questions still remain. What about computability? And still, I also haven't talked at all about sampling. Okay. Okay, so now let's get back to this general setting, right? We have MR manifold. We've got this probability measure on M, K convex hole, point in the convex hole. Okay, and the main result of this work with Nishith is that you can use the ellipsoid method basically to efficiently approximate this maximum entropy distribution by getting a solution to this dual program. Okay, and in order to do this, you need a few things to sort of we need a few assumptions. So the first thing is this mu needs to have some balance property. Okay, formally what this means is that the measure can't be too small anywhere. Basically, if you take some small ball, epsilon ball in the manifold, and you determine how much of the measure mu is there, it can't be doubly exponential. Basically, it can be singly exponential, but sort of no worse than that.
What measure?
I'm sorry?
It says small ball in what measure? In Euclidean?
I'm sorry, say it one more time.
What does it mean, a small ball?
Yeah, what
With
norm is
respect
the
to
ball?
what? No.
Yeah, a Euclidean ball. Yes, the RD Euclidean ball. That's correct. So I mean, most of this ball is going to be not in the manifold. So I'm sorry. So let me be a little more clear. You take a point in the support of the manifold. You look at a small Euclidean ball around that point. Of course, this manifold is going to be of potentially high codimension. So I mean, you're just going to be you're getting like a small ball. I mean, like here's your ball. A slice of it is somehow going to be where your manifold, and you just compute the amount of measure in that small ball, and it just can't be too small. But yeah, I mean, if you pick some random ball that's not kind of touching the manifold, of course the measure is going to be zero there. So you have to kind of center your ball at a point in the support of the manifold. Does that make sense? Okay. But what you want to think here is you want to think that the measure is uniform. Or I say symmetric here because if you have some kind of symmetry properties of this manifold, basically then you just have to kind of show this at one point, because then the measure is symmetric everywhere. And as soon as you can show this at one point, that's enough. And often these symmetry properties, I mean, sort of say that the measure is uniform anyway. And so like whenever you have some action on the manifold that preserves this measure, pretty much this balance property comes automatically. Okay. We need then also that A is not too near the boundary. The potential problems with this is that the entropy can get quite large and in a way that is sort of makes the dependence on A bad in that case. So if you're not too near the boundary. And also you need this strong integration oracle for mu, which basically just means you need to be able to compute this integral. You also need to be able to compute the gradient. But in most cases, if you can compute this, then you can compute the gradient. Like in most cases, I would say this is the case. And so it really boils down to being able to compute this function here. Okay. And so then the next question is, okay, fine. So we've basically boiled this down to being able to find these nice measures and being able to compute these integrals. But these integrals look potentially hard. When are we able to actually compute these integrals? Okay. And that's when symmetry comes in. So what we're going to focus on is we're going to focus on this case where M is some orbit of the unitary group in the space of Hermitian matrices. Okay, so let's fix some real vector lambda. Okay, and we're going to look at this orbit, which is just you take the diagonal matrix with entries lambda, and you look at all unitary conjugations of that matrix. Okay, now this is the same thing as just saying the set of all Hermitian matrices with specified eigenvalues. Okay, and what's nice about this situation is we have a Haar measure on the unitary group, and it immediately gives us an invariant measure on the orbit. Okay, I'm going to call it mu lambda, and because it's invariant under this action of the unitary group, like I mentioned in the previous slide, this pretty much automatically gives you the balance property. I mean, you have to still do some argument, but it's basically at this level of generality you can prove balancedness in general. Okay, so then the thing that remains is how do we compute these integrals? Okay, so let's look at a specific example and see how things go in that case, and then maybe we can see how to generalize beyond that.
You have a question?
Oh,
Is this just a polytope generated by the permutations of the vector lambda?
so well, this is not a polytope, but I mean, if you restrict to the diagonal of all of these elements, then you will get a polytope, which is exactly what you said.
The convex hull of this O lambda will be spanned by the
I see. I see.
mutahedron of lambda.
Well, it won't be a polytope, right? I mean, this is some orbitope. I mean, it won't be a polytope because you're looking at the convex hull of some orbit of the unitary group, but the eigenvalues will be in that permutahedron that you just met.
It's a spectrahedron. I think that's what I was saying.
Oh, okay. Oh, I thought he said.
So these type of orbitopes have a spectrahedral description as well.
Yeah. Okay. Okay. So let's look at a specific case here. Okay, this is the case that was exactly what we did in the quantum entropy situation. Let's let our vector lambda just have 1, 1, and the rest zeros. Okay, and so if you look at all unitary conjugations of a diagonal matrix with this diagonal, you're just going to get all rank 1 PSD projections, and then the convex hull will be all density matrices. Okay, and there's a sort of polytope connection here that we're going to exploit. I put this moment map here in quotes because I'm not going to talk about what this means or why I use this term, but there is some moment map on this orbit, which gives a very nice polytope. And if you don't care about this term, then just think about this very simple map that I've written down here. So here's what we're going to do. We have a bunch of matrices. I'm going to get a map to Rn by just restricting to the diagonal. So I have this matrix. I just pick out the diagonal entries and make that a vector. That's going to be my map. Okay. And in this case, we get something very interesting when we do this. Okay. In fact, the image of this acting on this orbit is just the standard simplex. Okay. And this is pretty straightforward because, well, this orbit is the set of all Hermitian matrices with these eigenvalues. Okay. So what does that say about the diagonal? Well, since the trace of all these matrices is 1, certainly the diagonal entries have to sum up to 1. And since all of these matrices are positive semi-definite, it means that all of diagonal entries are non-negative. Okay, and so these diagonal entries will be non-negative and sum up to 1. And this is precisely the definition of the standard simplex. So that shows that the image is contained in the simplex, and it's actually not too hard to see that it has to equal the whole simplex. Okay, but what's even nicer than that, okay, we have this nice equality. What's even nicer than that is it turns out that if you take this measure coming from the Haar measure and you look at the push forward through this map, you get the Lebesgue measure restricted to this polytope. Okay, and by Lebesgue I mean sort of like the codimension 1 Lebesgue measure. Okay, you get this Lebesgue measure restricted to this polytope, and more generally what that means is now if I want to compute integrals like this, I just have to be able to compute integrals like this. And it turns out that these are, I mean, you can write this down as some iterated integral. You can also do some kind of Fourier analysis techniques to compute these integrals. These are sort of easy to compute, whereas this, it's not clear how you would compute them. And this also says something kind of more conceptual, which basically is something along the lines of, right, if computing this is sort of equivalent to computing this, then it also sort of follows, once you think about it for a little bit, that computing Max-Entropy distributions in this case is somehow related to computing maximum entropy distributions in this case. Of course, the convex holes don't exactly connect, but there's maybe bijection was too strong here. Maybe I should not say bijection, but there is some very strong link between the distributions in these two cases. Okay, so in this case, we could compute these integrals. That's what we wanted to do here by computing some similar integral on a simplex. So how do we generalize this to other choices of lambda? Okay, well, we saw this connection before, right? There was some big connection that connected measures, computing integrals, Max-Entropy distributions. Okay, so now if we want to do this for other lambda, let's just kind of try to do the same thing we did before, right? So we have this moment map pi, we apply it to this orbit, and we in fact get this polytope that I believe Avi was talking about, which is what you do is now you take your lambda vector, you look at all permutations of it, and you take the convex hull of that. And basically, for kind of generalizations of the arguments I used on the previous slide, all the diagonals of elements in this orbit are going to be contained in this polytope, and in fact, you can show that they are equal. So, okay, so we have this situation where we have the exact same thing as before. We have this orbit. We look at this map. It gives us some polytope. Maybe everything's going to work out. The problem here, though, is we don't get this same nice thing as before. The push forward of this Haar measure that comes from the unitary group is actually not quite Lebesgue measure, but only a piecewise polynomial density times Lebesgue measure. Which maybe, and this is a very famous thing called the Douster-Heckman measure, or the Douster-Heckman theorem. Okay, and maybe this seems okay. I mean, piecewise polynomial, how bad can it be? The problem is I'm not exactly sure how bad it can be because I have a hard time even computing very simple examples. It seems like most of the formulas involved with this are very difficult to get your hands on. And so, I mean, like, I don't really know what to do about this. This seems like a hard thing. If someone knows how to compute these things, that'd be great. I'd love to talk to you, but it seemed very difficult. Okay. And in fact, though, there is a fix that's possible. One can sort of choose a slightly different map here and go to a different polytope and do something there. I'm not going to talk any more about that. In fact, I would, if you like this idea of kind of mapping things from manifolds to polytopes, I'd recommend watching Colin's talk next, where he should, be talking a little more about this other option here. But we didn't do this. Instead, what we did is we kind of avoided this whole polytope connection altogether, and we just in fact found a formula for this integral. Okay, and basically where it comes from is this thing called the HCIZ formula. Okay, and this formula, what it gives you is you have some integral over the unitary group of some log linear thing related to some Hermitian matrices A and B, and it gives you this really nice formula for these integrals. Right, this is somehow just a determinant and some products of differences. Okay, and so when you take log of this, you're going to get some just sum of kind of factors. Okay, and maybe it's not immediately clear why this would give you an expression for this integral, but the way it's actually quite simple once you kind of write it down. But the way maybe you can see it here is if you look at this UBU star that's appearing, somehow this integral is going over all conjugations of this matrix B. And so what can sort of happen is you can kind of replace this B with, you know, some maybe other variable that you're taking an integral with respect to, and that's exactly kind of how this X appears here. Okay, so this is sort of a different integral, but actually these are equal for pretty straightforward reasons. Okay. And so, okay, so we at least found some place maybe where we had the ability to compute these integrals, right? That was even a question at the beginning. Can we compute these integrals ever? Okay, now we have some situations. We have these orbits of the unitary group. Okay, but why do we care, right? So we can do this. We found something we can do. Why should we care to write this down? And also more generally, like, okay, we have this maybe somewhat specific case of unitary orbits. Can we do something a little more general than that? Okay. So right on the previous slides, we saw how we can compute these integrals for these orbits using the theorem I stated from before. This implies an efficient algorithm for computing Max-Entropy distributions on these orbits. Okay. And so now the question is, where do these appear? Well, the first case we looked at was this case where we looked at the orbit of this matrix with one eigenvalue 1 and the rest 0, and that we knew already that was equivalent to quantum entropy. Okay, so we saw that before. Generalizing this, instead of just looking at E1, if we look at the sum of E1 through EK, so this means all the matrices with K eigenvalues equal to 1 and the rest 0. Okay. This problem then, right, the manifold you get out of this is the complex Grassmannian. And so this whole process then yields maximum entropy distributions on a Grassmannian. And if you care about Grassmannians, maybe this is just in general kind of an interesting thing that you can do. You have these sort of canonical measures on a very well studied manifold. But also these are utilized in certain low rank approximation algorithms, especially when you care about privacy, because I mean, essentially, I mean, maybe I'll let, this is a part of our later work with Colin, and so maybe I'll let him talk about this. But somehow, right, if you want to pick out the dimension K subspace corresponding to the top K eigenvalues of some matrix, and you want to do it in a way that, in a random way that doesn't kind of give away the matrix structure, then maybe what you could do is look at these max entropy distributions and sample from the one associated to the particular matrix you started with. And like I said, that's in our future work, and I won't say any more about that. It turns out that these specific cases, sometimes these complex Langevin distributions are precisely distributions which come from these orbits, and these are studied in statistics. And also this density on the unitary group, this thing that we are taking an integral of in the previous slide, these are things that are called HCIZ densities, which I believe Colin will talk about a little bit more as well. These are used all over the place, physics, random matrix theory, and actually, generally speaking, even beyond his talk, I would recommend talking to Colin about these things. At least in my interaction with him, he seemed to have quite a wealth of knowledge when it came to this. So I'd recommend talking to him, or asking questions in his talk. Okay, and the other question I wanted to answer here was, what about other manifolds? Okay, so we need some kind of, right, what do we need? We need some kind of measure, maybe via some symmetry on the manifold we were looking at, and we need an integration oracle. Okay, and so we talked a little bit about polytopes that come from this entropic barrier function. That could maybe be one option, right, with the Lebesgue measure. But kind of the main generalizations of this that at least I know about is in some other work with Nishith. So this is a different paper than the one I keep referencing, where we're able to extend a lot of this to adjoint orbits of compact Lie groups. Okay, so you kind of have a Hara measure coming from the compact Lie group. It goes to the orbit. This HCIZ formula extends to that case. And I wouldn't say, I don't know if there's any kind of like really explicit applications of this. So I'm not going to talk too much about it. But it is really interesting how a lot of the Lie theory has to come into play to sort of prove all the different points of what's going on. So I think this is a pretty interesting paper just because of its connections between Lie theory and some of this entropy, these max entropy distributions. Okay. Okay. So let me conclude. So in this talk, what did we talk about? So first, I kind of gave an overview of discrete maximum entropy distributions and a number of the applications that came from those. So things to combinatorics, discrete approximation, orbit problems, norm minimization, statistical models. And then I talked about continuous max entropy distributions, which had a number of kind of different applications that are sort of a different quality. This quantum entropy, interior point methods, low rank approximation. Okay, and the specific examples we looked at were these conjugation orbits of the unitary group. Okay, and the point was here, especially when it went to this continuous case, was, right, you have this integral you have to compute. That seems intractable, at least a priori, but the point is that the symmetries of the manifold gave rise to not only the measures, but also ways to compute these integrals, which made the computability of these max entropy distributions possible. And so there's this question that I kept asking about sampling, and I never answered it. And so all of this is just to, convince you to watch Colin's talk after this, where he'll be talking about sampling from these distributions. And also, finally, there's a couple open problems. Most of them, or these two, are somewhat conceptual. The first one is something that I have thought about somewhat. It's something I really wish there was an answer to. So in this discrete case, there were a lot of combinatorics applications. You could get certain bounds on things. You could approximate certain quantities. And in the continuous case, we did have this quantum entropy that you could approximate. But are there any combinatorial applications that come from the continuous case? This I think is some kind of I don't know. I expect there to be some kind of strong link between these two, but nothing like this seems to appear in the continuous case. And also, there's this kind of conceptual open question I asked near the beginning of the talk. There's this whole other generalization of the discrete case to invariant theory, norm minimization algorithms, things like this. And then we have this generalization that's very much about entropy and maximizing entropy. And I've thought about this also quite a bit. I don't see a connection. There are little wisps of connections, but it's unclear exactly how connected these two generalizations are, or if they're just kind of completely different. Okay, and that's it. And thanks for listening.
Okay, questions?
Yeah.
Okay. Can you hear me?
Yeah, I think so. Yeah.
I don't know if maybe this way maybe it's better.
Yeah.
So hi, very
Hi.
nice. So I had several questions, but so let me begin with a question which was what is because you say we can accurately approximate. So the approximation, you measured it how? So with the difference with the objective function, or
Yeah, that's correct. Yeah.
Okay.
You can get within epsilon of the objective in like log 1 over epsilon.
Okay. And so the other question was if you want a bit more general. So basically, so as you said, you're doing Kullback-Leiberg divergence minimization under a linear constraint.
Yeah.
Which so the dual is very nice, but so you have just one constraint, but this duality usually, so it's more general, and you can add as many linear constraints as you want. So
Okay.
my question is, could it make sense to not only fix the mean, but or also fix I don't know, the variance or something like that?
I fixed the mean, but also, can you say again?
Yes. So does it make sense to fix not only the mean, but also the variance or the covariance matrix or something like that, and then you maximize entropy or something like that? I don't know.
Yeah. So I'm not sure. I can say one thing where maybe what you're thinking of is the case of how the Gaussian maximizes entropy when you fix the mean and the variance. And that case sort of corresponds to if instead of looking at vectors in Rn, you look at rank 1 vectors by sending V in Rn to VV star.
Yeah.
then kind of the variance constraint in Rn corresponds to a mean constraint in now this PSD cone that you're looking at. Right now, your convex hull is the PSD cone. So I don't know in general about adding a variance constraint, for instance, but there are under certain circumstances, there are ways to encode the variance constraint as a linear constraint by making some transformation like the one that I just mentioned. I don't know how far that it generalizes, but I've really thought a lot about this kind of linear constraint case and maybe not so much about anything else except for these ways to transform kind of between cases. So I'm not sure, honestly.
Any other questions from the audience? How about the online folks? Anybody online want to pipe up? I have a question.
Sure.
You mentioned this constraint that this point is not too close to the boundary.
Yeah.
Of the convex hull, right?
That's correct. Yeah.
So I know that like Nishith has some other work and Damien that where they somehow get around this issue in the discrete case. Is it sort of intrinsic in the manifold case that that's like a problem, or do you think you can get around it somehow?
So, okay, that's a great question because you're exactly right that in the discrete case, Nishith and Damien have this work that gets around. I don't know if it's intrinsic. So I think maybe for certain manifolds, it might be intrinsic. Like I don't know, but I will tell you the reason why the stuff that Nishith and Damien do can't apply to this. Because basically what they find out is they show that like, even though the optimum keeps getting like basically goes off to infinity, the objective function sort of doesn't get too much smaller after a certain point. And so even though you're maybe really close to the boundary, and the optimal input is getting going off to infinity, you can actually go very, very far away from the optimal input and still get an approximation. And they measure this by looking at kind of like they look at the convex hull and look at the facets of the polytope. For cases like say the sphere, like looking at continuous Max-Entropy distributions on the sphere, I kind of expect. So first of all, you can't do this because as you're not, there is no like bound on kind of on your objective function. I mean, as you're going to the boundary, you're going to infinity. There's really kind of no way around this. And especially because there's no like, I don't know, geometry to kind of maybe help you in the sphere case. I would expect this to not like this to be an intrinsic issue. But I'll be honest with you, I'm not really sure. I've only thought about the fact that you can't use what they did to kind of fix this problem. But beyond that, I haven't been able to figure out like what could you do to try to fix it. It looks intrinsic, but maybe not. I don't know.
Thanks. Okay. If there's no other questions, let's thank Jonathan again for a lovely talk. And I guess we resume again at 11.